There we go. Let Emma in. Oh, right. I think everybody's there. 16. Joey. And somebody else. I don't know. So we'll leave that there. I'm sure there might be someone. I'll let you write that down. I mean, I don't necessarily really need to because I'll post this again when we are finished. Hopefully, if you had any questions with the factorial stuff that we did, come on, Brain. Then, like, you can message me or something like that. I think because there hasn't been any sign of movement, I'm going to have to post an assignment on here, which I didn't really want to do, but it will be relatively short just so I have something to say that, hey, you did something and all of that, but that will come, well, tonight or tomorrow or who knows. Because I haven't heard, technically I think marks are due, I don't know if they're due on the 5th or the 8th or the 9th or something like that. I'm going to check that out. Suppose if I give an assignment, the odds that it's done, all right, well, whatever. Well, I'll figure that out hopefully tonight. And I don't feel like crap tomorrow. But the Wi-Fi reception with the 3rd dose is really good. I'm just kidding. You don't get Wi-Fi from a needle. We talked yesterday and the day before about permutations and factorials. We're going to look at permutations again, but if we have a number of permutations of 7 people, or well, 16 people, we can just do that with a straight factorial. But what happens if I only want to pick 3 of you? And whoever's name gets randomly chosen first gets $100. I don't have $100, I'm sorry. The person who gets second gets 10, the person who gets picked third gets 1. Well, the order in which you're chosen matters, essentially. And we're not choosing everything. So we have this nPr function where, whoa, sorry, apparently I didn't pick my pen up. N objects, so if I was talking about you as a class, right now there's 16 of you, so N would be 16. We're only taking 3. So if I decided to do that sort of thing, I would have to do 16 factorial over 16 minus 3 factorial. And we would work that out, and we'll look at a couple of different things. When you get to really big numbers, I said, hopefully you have a handy dandy, like any scientific calculator, except for this one, that has sine, cos, and tan, normally has an nPr button and an NCR button, permutations and combinations. We'll get to that later. But for whatever reason, when they redesigned the Windows calculator a few years ago, they decided that those, because I haven't found them in any of those, it's a real pain in the ass. So I have to bring up this stupid one where, like, it's just I have other calculators, like physical calculators, but to put it up on a screen, I can't do. I haven't, and now that I can't download anything that I want without grief, it's a bit of a pain in the ass. So we're going to go through with this. Solve using permutations. Luke downloaded 10 new songs picked 10 new songs to put on a Spotify playlist. He created a playlist of 6 of them. How many different 6-song playlists can he use? So, well, in this case, he has 10 songs to choose from, and there's 6 of them. And the order in which you place them is apparently important. This is, in hindsight, the best example. nPr is n factorial over r factorial. But this is where order of operations comes into play. 10 factorial over 10 minus 6 factorial. Just putting numbers in. Well, order of operations. Factorial is a multiplication. So it comes in order of operations after brackets. There's no exponents in here. So we need to evaluate this bracket first. 10 minus 6 is 4 factorial. It's 10 factorial. Now we can kind of do what we did the other day. I'm going to do this for the first one. Well, this is 10 times 9 times 8 times 7 times 6 times 5. Over. That was all right. Well, go away, go away, go away, go away. So it would equal 10 times 9 times 8 times 7 times 6 times 5 times 4. I'm going to, I could, if I was 10 factorial divided by 4 factorial equals, in this case, it's 151,200. This is the crappy part. If we were sitting in class, I would be able to go around and check a whole bunch of people's calculators, because the problem with calculator logic is there's like 4 or 5 different ways to put these in. If I'm doing it here, whoops, 10 songs, picking 6 of them, and watch this, and it's going to load. nPr 10 factorial over 10 minus 6 factorial, 151,200. Kind of a side note, some people will look at these like this. 10 songs for the first, 9 for the second, 8, 7, 6, and 5. The number of songs that you can choose from if you're only playing them once. Well, they're the same thing. Where these are going to come into, like 10 and 6 is, like if you did that on a test and wrote out an answer, well, guess what? You figured it out. It's technically not incorrect. But if you want to do a giant password, and we're going to look at just different types of passwords that are possible, the bigger the number, the more of these that it's going to be, the less likely you're going to want to do it this way. This is kind of a side note, defining 0 factorial. What happens if n equals n? No, n equals r. Stupid. So if those are equivalent, we would have n factorial. Well, if n equals r, this is our formula, then this is going to become like that's where this is going to be. Well, what's n minus n? That's n factorial. N minus n is 0 factorial. Can I divide anything by 0? No. But I can, like, this is one of these, 10, 10. Gives me a value. 10, picking 10 gives us a value, because going back up to here, well, this would be 4, 3, 2, 1. Well, that has to have a value. So if this expression has to have a value, have a non-zero value, and in fact, np10 well, 0 factorial, and that's what that equals. Let's see who's Owen. There we go. We're just about, this is kind of an aside. It's not super important, but 0 factorial has to be 1 or none of these nPr formulas are going to work. And if they don't work, that none of this makes sense, but it all logically does. All right, so passwords. And here's where this hands and cards, well, hands and cards is a little bit different because the order doesn't matter, but in a password, the order in which you put your characters in is important, because if your password is 12345 and you enter 54321, it's not going to work. So the amount of possible passwords is quite large. So an online store makes users register a password between 5 and 7 characters long, any digit from 0 to 9, and or any letter of the alphabet. The passwords are case sensitive. TO. Well, there's 10 digits. There's 26 lowercase. I don't know what's going on. 26 uppercase. Well, 26 and 26 is 52, and 10 is 62 total characters on a keyboard. And then if you, like, we're just for this example going to limit it to letters and numbers, but I'm looking at a keyboard now and I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 15, 16, 32, give or take, other characters. So add another 32, that's 94 characters. So this is why, well, we'll look at just in a second. So this 62, this represents our n. So n equals 62. If it's a 5-character one, r equals 5. 62 characters, if you make a 6 password, 6 one long, it's 6. You'd have to do 62, 7. So your password is one specific thing. To crack a password, you have to try all these different permutations of these numbers. So this one would be 62, capital P, 5, which is 62 factorial over, nope. And we don't technically have to do this. I'm just doing this to show you 5, that's 2, 3. And I'm not going to write that out. I'm going to pull up this handy dandy web page. Clear. 62. Pick 5. Holy. 776-520-240. Let's see if I can remember that. 776-520. So there's 776 million possible passwords with 5 characters using just letter and lower and uppercase numbers. Well, this one is 62P6, blah, 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 do the same thing. Holy! I went from times 10 to the power of 8 to times 10 to the power of 10. 442. Wait. Oh, B. Let's big money. Copy. Paste. Sweet. Blam. Saves me all sorts of stuff. So this was 7.7 times 10 to the power of 8. This is 4.4 times 10 to the power of 10. This one should be bigger because obviously you have more possibilities. Times 10 to the power of 12. I'm just going to put it way up here. There we go. 2.5. So that ends up actually being like 2.6 times 10 to the power of 12, give or take. 2.5 exponent of 12 plus 4 exponent of 10, and this is just a ballpark. 2.54, because it's one of these, or means add, or means add. There's that many passwords if you limit it to that. Why does everyone want to add one of those? What did I say, 32 characters? Because then n becomes 94 if r is 6. If you make a small 6-character password, wow, not 994. I don't even think this would be able to do that. What did I say, 6? So 6-character passwords, we got 5.8, 5.9. So we add another 1 point. It seems like, oh my gosh, it's only 1.5, but it's 1.5 times 10 to the power of 10, which is 15 with 9 zeros after it. That's a lot of possible passwords. But then you think you can write a program to check all of these permutations, and your computer can generate something like times 10 to the power of 10 of them a second. So, yeah, passwords are secure, but they're not that secure. But that's the idea and the power of these. I don't want to have to write all of those out. I don't want to have to do 62 times 61 times 60 times and whatever. I can just use that calculator to go from there. That takes a little while, so I'll let that isn't totally necessary to write down. Okay. 19 minutes, okay. We're almost done. Now comes 2 different things. A used car lot has 7 different cars. They want to park on the side of the road for viewing. 3 red cars must be parked so that there's a red car. Oh, why don't I do it this way? A red car. Sorry. So this is the way that they have to be parked. So it kind of is a little bit counterintuitive, but we have, whoops, the red cars, the other cars, right? So the red cars, how many red cars are there? Well, there's 3 red cars. How many are we choosing? 3. So if we did this as factorials, that would be 3p3, which is not going to be super exciting. 6. Not all that much fun. How many other cars are there? Oh, there's 4 other cars. We're picking 4. Oops. P4, which is 24. We want this and this, so the total is 6 times 24. 625 is 150, less 6 is 154. No, 150 less 6 is 144, stupid. Now, if we look at it the old-fashioned blank way, how many red cars are there? Well, there's 3 to choose from here. How many red cars are there to choose from there? 2. How many red cars? 1. Oh, I want a different color. I don't want that color, though. Sorry. 4. Then there's 3, and there's 2, and there's 1. We should have done the red cars in red. Stupid. 3 times 2 times 1 is 6. So the red cars is the 3p3. 4 times 3 times 2 times 1 is 24, which is 4p4. So people write stuff down before you carry on. So far, so good. I hope so. The red cars, the 3 red cars must be parked side by side. This is one example because the red cars could be here, or we could have black, red, 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 so on and so forth. So the 3 red cars are there. Well, that is well, there's still there's 3p3 ways to do that, which is 6. Those other ones is still 4p4, which is 24. But there's another thing we have to worry about. There's 1. Let's switch colors. Stupid face. 1, 2, 3, 4, 5. Because we could have the reds, or I could have hopefully that doesn't cause too much trouble. Or I could have one of those. The red cars. So because there's this idea, in this case, now we have the different arrangements. There's actually 5 different ways to arrange that. We have to do all of these. We have to multiply all of that together. 6 times 24 times 5 equals. Why is that just 5? Well, because I'm moving this. It could go in here. It could go in here. Or it could go there. And though, like, there's no other way to you account for the other cars to be in a different order separately. So that's kind of a quick and dirty introduction to permutations. 5, 6, 8 to 11, 13, 15, and 17. Yeah, you can use your calculator. 5, now your girls are doing 3 positions: center, wing, and defense. Order matters. If only I could remember things. 5, 6, 8 to 11. 5. 6. 15 people for 4 positions. 5,000 tickets for a draw. You assume there's 3 different prizes. How many ways are to do that? Social insurance number. If a Canadian social insurance number begins with the digit 6, that's interesting. This one is kind of the space idea. Basketball team, each position is different. The 5 tallest, the tallest is in the center. They're starting 5 players of Sandra and I can't remember again if those were questions I want you to look at. Come on, brain. 11, 8, 10. That one's all right. For each expression, state the values for which the expression is defined. What? Well, that's just simplifying those. That's okay. 13, 5 different graduation scholarships for 20. Nobody can get one if there's no limit to the number of scholarships. That makes things a little different. Those ones are kind of optional. Not necessarily that those ones are optional. That's what I kind of figured. So puts us about half an hour. We'll look at tomorrow objects that are identical. Then we move into combinations. And hopefully we'll have some direction as to how long we're back. And now this image is way down there. Nuts. I'll deal with that later. So if you give those questions a shot, I'll download this. And if you have questions, you can give me a shout, let me know. And if not, I'll put an assignment up here shortly, and have a good day. Bye. See ya. Leaving, leaving, leaving.